Advanced math problems move away from the standard coordinate grid, instead representing vector journeys across labeled geometric shapes. These problems require calculating pathways using algebraic logic rather than counting squares or measuring lengths. Exam papers use bold font to identify vectors. When writing answers on paper, this notation is represented by a single line drawn beneath the letter. Converting these physical lines into algebraic terms allows us to solve for missing dimensions using a repeatable set of geometric rules. A vector describes a journey between 2 points. Here, the journey from x to O is defined by vector A. If taken in the opposite direction, starting at O and moving to x, the algebraic sign is reversed, making the vector negative A. This relationship is illustrated here. On the right, vector B has the same magnitude as vector A, but because it points in the opposite direction, it is defined as negative A. We can also change a vector's magnitude using a scalar multiplier. Vector A can be scaled up to 2A or reduced and reversed to negative 1/2 A. If the original value of A is 12, multiplying by negative 1/2 results in negative 6. The arrow indicates whether the algebraic sign is positive or negative, while the coefficient tracks the physical scale of the journey. To find an unlabeled path, detour along known vectors. Traveling x to O against the arrow gives negative A. Moving O to Y with the arrow adds positive B. Summing these gives negative A plus B, simplifying to B minus A. Summing the algebraic values of known detour segments allows us to map any unknown journey on a diagram. Let's apply this logic to a parallelogram where only 2 sides are labeled, 2A on the base and 6B on the left side. By definition, opposite sides of a parallelogram are perfectly parallel, meaning they share the exact same vector. The top edge is parallel to the base, so we label it 2A. The right edge is parallel to the left, so it's 6B. Identifying parallel properties provides more labeled segments to use when calculating a detour. To find the vector to midpoint M, we detour from O to A, giving our first term, 2A. Next, travel from A to M. Because M is exactly halfway along diagonal AC, and AC is parallel to 6B, the vector AM is 1/2 of 6B. Using brackets for fractional substitutions ensures the scalar multiplier is applied correctly. Half of 6B is 3B, which we add to our first term to reach the final expression, 2A plus 3B. This process of applying a scalar to a known diagonal allows us to accurately map journeys to internal midpoints. Starting with just 2 labeled sides, we have calculated the algebra for every boundary and an internal midpoint. These solutions are achieved by applying 3 steps, using indirect detours, reversing signs when moving against arrows, and copying vectors across parallel lines. To practice these rules, pause the video here and try to find the vector for the journey from P to Q on this diagram. Combining detour summing with scalar multiplication provides a methodical way to deconstruct 2D vector geometry problems.